This is a video on system synthesis from a signal flow diagram, and it's basically going to be the simplest circuits with the simplest signal flow graphs that I can find. And so a lot of this you already know. For instance, this in the signal flow graph, you have a summer, and you can have addition and subtraction in a summer. You already know a circuit for that. This is what I call the advanced summer, right? And you can add and subtract with arbitrary weights as long as we meet certain conditions, which I won't go into here. But if you don't know the advanced summer, well, here's an inverting summer, right? That goes into another inverting summer. And so we sum we subtract signals 2 and 3 with some weights. But then we subtract 1 and 4, but then we multiply the gains by another -1, so we add, right? Then another part of the signal flow graph is something in a box, and it's some kind of transfer function. So some we already know, right? We have gain times omega naught divided by S plus omega naught. Now, yep, we can review that. Omega naught is in a first order circuit is going to be 1 over R over C, right? And the gain in this case is a non-inverting OPAMP, right? We have the high pass version of that, where we just reverse the capacitor and the resistor, but we still have our gain, right? And we can set the gains here independently of the cutoff frequency, right? We have other transfer functions that we know. Minus G over S, right, where G is 1 over RC. That's an inverting integrator. If I wanted to make it non-inverting, I could add an inverting stage. And that's actually about this here, and telling you to add another stage in series is actually on the next slide. And then there's some other things where we have an RLC, and I'm trying to say this as succinctly as possible. Because these are all in series, no matter where I take the outputs, across the resistor, across the inductor, and across the capacitor, the denominator is going to be S squared plus R over L times S plus 1 over LC. And this is a good time to point out that these notes are really kind of an emergency level of note before I write things a little more formally, but I'm a little pressed for time. So if I want the numerator to be 1 over LC, I take it across the capacitor. If I want S squared, I take the voltage output across the inductor, and R over LS I take across the resistor. Now you don't have to take it off differentially, you can just move things around. Also, if I go from here to here, I can sum both of those. So you can also put a gain stage after it, right? So you already have seen second order circuits like this, okay? We're just really talking about it in a different way, all right? Now, if you've seen it, but it's a little hazy, that's okay. We're all a little hazy sometimes. Now then, for signal flow diagrams, we have series. And we have H1 goes into H2, goes into H3, and that's easy to find the transfer function. It's just H1 times H2 times H3. OPAMP-wise, that's just, I'll do minus plus. Right, this has a transfer function, if it's ideal, of minus this resistor divided by that. And then this has a transfer function of this resistor divided by that minus. And when you multiply them all together, you get positive. So if I just put in some numbers, I basically get R2 over R1, R3, that should have been 4, and that should have been 3. Excuse me. So that would be the transfer function. Now, yeah, you can have filters in here. You know, anything that goes inside that you can have it. But basically, just putting things in series, you know that these op-amps separate the circuits, if you will, so that you can get these discrete transfer functions. So what's new is trying to remember all of our op-amp configurations and then just lumping it in this box, right? In this case, I could say that's minus G1 and that's minus G2. And I don't have time to do an H3. All right? Now parallel is just summing. So you can have transfer functions here and 3 inputs go into a summer. In this case, I arbitrarily said plus, plus, minus. Right? So I get input 1 times H1 plus input 2 times H2 minus input 3 times H3. Now, yeah, what is that summer? Well, it's one of these. Okay? Subject to special conditions. So really, a lot of this is you will have been exposed to this before. Again, if you're hazy, it should be relatively quick to get you back up to where you feel comfortable with it again. All right? So, now we have the series and the parallel, but now what you haven't seen, right, is feedback. Now we have a summer here, and we know what that is. It's just a summer circuit, right? H1, we know that can be an RC with an op-amp, RLC with an op-amp, and pulling the output off the resistor, the capacitor, the inductor, whatever. And we have another H2 here. Sometimes that's called G, right, because it's on the feedback, right? And it's going to be negative feedback, so we're going to take the output, multiply it by something, and then subtract it from the input. Now, how do you... so while you might want to go from the equation to the circuit, it's better to learn it going from the signal flow graph forward. So what we do is we just say, all right, I have, what is V out? All right, out equals what? Well, it's going to be in times plus 1. And yeah, I could have a scale factor here if I want it. I can put a scale factor in the summer, right? This is design. There's so many ways just to do anything. You basically have to try it more than one way and then see which one is the best for your particular situation. And yeah, usually minimizing the number of parts is a good way. So n comes in, it's multiplied by 1, in this case, times H1. So that's H1 times n. Now how do we deal with the feedback? Well, I'm starting at out. Okay, there's my out. Then I get multiplied by H2. Great. Then I'm subtracted or multiplied by minus 1 or subtracted, right? And then I multiplied by H1 to get back where I started. All right. Then we combine the terms out. 1 plus H1 times H2 equals H1 times the input. And then we solve for the system transfer function. All right. So you can have systems with multiple feedback paths, but really, this is what we're going to talk about just now. All right. So let's do an example where H1 is omega naught divided by S plus omega naught times a gain, and H2 is the same, but it's got a different cutoff frequency and a different gain. Oops. Right? So again, I'm just redoing this where this is our transfer function, but now I'm substituting things. And this is just some algebra. All right. And so in the end, we get our numerator and we get a second order system. And with careful selection of gains and omega naught and omega 1, you should be able to make it over, under, or critically damped. Maybe not easily, but you should be able to do it. All right, so now let's turn this into a circuit. Well, what's H1? It's a low-pass filter with gain. What's H2? Low-pass filter with some kind of gain. What's the summer? Well, we have the input, and then we're going to have this feedback. So we have two inputs here. All right. So let's put it all together. I like to start with the summer. Okay. So here's the summer. My input comes in. It's on the positive side. And yeah, with an advanced summer, I'm going to have to balance that if things aren't quite right. Right. Then it goes into H1, which is this low pass filter. I got, all the resistors labeled. Then I go into another low pass filter. But actually, out is coming from here. In the other picture, I kind of had H2 over here in the feedback, but once you start drawing the circuit, it's just kind of easier to go along this way. And then I take that feedback and bring it right in here. So my gain 1, whatever that should be, is just 1 plus R3 over R2. So really, you need to know two resistors, but you've only got one equation. And so really, you can solve for R2 or R3, but you're going to have to choose one. I tend to choose 10K, but sometimes I might solve for a resistor that's over a meg. Well, then I go back and lower that, right? Talking about ideal op-amps, they can't drive small resistances, right? These are limited to about 40 milliamps. And large resistances like a mega ohm and over have issues as well. I'm not going to get into it here. But, that's a good place to start. Probably, if you can avoid it, don't go below 2K. All right. As you look at the gain bandwidth, the open loop gain on these gets smaller when you have a load resistance of 2K. All right. And so you have an R1 and a C1. And yeah, how do you choose? Well, what you do is you choose a C1 first, and then calculate what the R1 should be, and make sure that it's, not too big, not over a meg, and not too small, not less than 2K. Now, sometimes you have to go less than that, but a lot of things have 50 ohm series resistance coming out. So you want to be 100 times bigger than that, right? Otherwise, you're going to get a voltage division. It's like a non-ideal voltage source, right? So, you can choose 1 micro or whatever. There's some notes, and there's some common ones you choose because there's always more choices of resistors than capacitors. Okay, and so this one will have a different cutoff frequency. Now, yeah, what I would do is choose the same capacitor and then calculate different resistors. I would try to keep the same feedback resistor, right? Make all of these 100K, make that 100K, and then, calculate these ones.
Dinner, sir.
And that's it. Dinner is served. This should just get you started until I can get some better notes together. But I know a lot of you like to get ahead, so there you go.